Welcome to the webinar on what's new in Itasca Software version 9.2. This is Jim Hazzard, Software Development Manager at Itasca. So first, just a few words about point releases. Version 9.2 is our second point release. We did a version 9.1 about 6 months ago. This is a little bit of a departure for us. Traditionally, we've just done major releases approximately every 3 years. The purpose of these point releases is to try and get new features out to the users faster. So rather than having to wait around for 3 years for a major release with a whole lot of things in it, the point here is to push out smaller releases with maybe less things in it, but do it faster. So you can get these new features faster and start using them rather than having to wait for the next major release. A couple of notes. These point releases are only available through subscription or a maintenance plan. And another important note is that these are basically the same as big releases. They just maybe have less stuff in them. And so what that means is that any of the data files you have from old versions will run in these point releases. Any of the save files that you have from old version, you will be able to restore in these point releases. So there's really no downside to going to these new versions. You get the new features, and everything that you used to have still works. Okay, so what's new in 9.2? One of the major new things is cluster computing. This is something we've been working on for a long time, and we're finally making it available to people. And what this is the ability to take a FLAC 3D model and divide it up onto multiple computers and have each one of those computers do its own calculation, and yet have communication between them. So essentially you have one giant model being run on many computers, and it allows you to run the whole thing a lot faster. Okay, so you can see here the plot on the top right. This was a relatively simple model, although it does have 8 million zones in it. And you can see how the calculation speeds up as we add more nodes to the cluster. And so the top data point here, we had a cluster with 24 nodes on it, and the model ran a little bit more than 16 times faster. So it's not linear, but it's pretty good. Being able to run a model 16 times faster than you could yesterday is quite significant. For a more realistic model, so this is one of the models from one of our consultants, some sort of realistic open pit with densifying and attaching and joints in it and so on. We ran this on an 8-node cluster, and it went about 5 times faster. So again, still significant. Imagine a big model that maybe takes a week to run now. You could potentially run in a day instead. So just a little detail on the way this works. The whole model is still constructed on a single computer, and let's call it the head node. So the head node needs to have the entire model. And this is the same as you would do now. And so all of the model building and construction and so on happens on a single computer. It's when you start doing the calculations, when you start cycling, then the model gets split up and distributed to the nodes. This happens automatically. You don't need to tell it where to do the divisions and so on. It just intelligently divides up the model and puts different pieces on different nodes to try and balance the load, so to speak. Each one of those nodes is responsible for solving part of the model, and then there's communication between the nodes at the boundary between these pieces. So it certainly helps if you have a fast interconnect between the different nodes. So this carries on, and then when cycling finishes, the head node brings all the pieces back together again to create one big model and one save state. And so this is important because then you maybe want to look at the save state on a regular computer. You don't need a cluster, and do all your plotting and so on, just like you normally would. So, okay, you want to do cluster computing, but you don't really know the mechanics of how to do it. You can, of course, build your own cluster, and a lot of universities probably have clusters in-house. Most consulting companies or engineering companies probably do not. So second option would be to configure a cluster on the cloud. So you can do this. You can have an AWS account, and you can go and set up a bunch of machines that form a cluster on AWS. And this is possible, although admittedly a little bit tricky. So we have option number 3 here, for now, we have a partnership with a company called Rescale. This is a third-party company that makes it easy to do cloud computing, okay? And it's especially easy because we have a partnership with them. And so they have the ITASCA software already preloaded onto their systems. And so what you can do is you set up an account with Rescale. You essentially give them your credit card. And then there's just a very easy click-through interface that allows you to set up these clusters. So you specify your input, whatever data file you've got. You choose the software, which is just going to be Itasca. You choose the hardware. So you need to choose, how many nodes and how much memory and all this kind of stuff. And then it automatically just builds that cluster for you on the cloud. You don't have to worry about the details. And then you say go, and it goes off and does the calculations for you and creates a save file, and then you can get it at the end. Of course, you can watch it go, and you can see what's happening as it's going and so on. So it's a fairly sophisticated platform to just make it easy to do this kind of cluster computing. And we've created a little video to show you how to do that stuff. Okay, now just a little bit more about the cluster computing. Not everything that you can do in FLAC3D you can do on a cluster. Setting up all these communications and things is a little bit difficult, and so we haven't got all of the features working yet. Mechanical calculations are working, fluid flow and thermal calculations are not. But if you want to do a mechanical calculation, almost everything related to mechanical is there. You can do joints, you can have zone joints in there, you can do apply, relax, you can do backfill, you can do dynamic analysis, including all the different types of damping and all the boundary conditions. Even though you can't do fluid flow, you can have pore pressures. So you could specify a water table or similar to set up pore pressures. You can actually have changing pore pressures due to mechanical effects. So this would be an undrained response. That all works. Almost all of the fish will work on the cluster, including fish that is executed during cycling. All the constitutive models work. Factor of safety analysis works. And I put in red here at the bottom. Our goal here was to make it as easy as possible for people to run on a cluster. And most of the time, if you have an existing model that meets these criteria, you can run it on the cluster by adding just one line, which would be model configure cluster. And then what it will do, as soon as it starts cycling, it will intelligently divide up your model onto the nodes, do its calculation, and then bring it back together again at the end. And you really don't need to worry about the details. Okay, how does the sales work? So the cluster computing is built into regular old FLAC3D, so you don't need a special version or anything like that. All you need to do is buy the option. We have 3 choices here: the basic option up to 8 nodes, advanced up to 16 nodes, or professional up to 32 nodes. If you want more than 32 nodes, you're going to have to call us. If you want one of these options, you can go to the website and have a look at the prices. It varies a little bit depending on your region. So I haven't got it on this slide, but you can go and look at the prices on the website for these different options. And again, all you need to do is buy the option and you can run FLAC3D on the cluster. You don't need a special version or anything like that. And again, we've tried to make this as easy as possible for people. Okay, that's all I'm going to say about cluster computing. There is a chance to ask questions at the end of this webinar, so I encourage you to do so if you have more questions about this. All right, other new features. Couple of slides here about constitutive models. So we've added a curved Mohr Coulomb model. So you will all be familiar with the regular Mohr Coulomb, which is just a straight line failure envelope. A lot of people want to do something more complicated than that, maybe like a bilinear envelope, or maybe a trilinear envelope, or maybe a curve, like a Hook-Brown style thing. So we've created this sort of generic Mohr Coulomb that allows you to create more or less whatever kind of curve you want to define the failure envelope. So you can give a function that specifies a curve, like a smooth curve. This left plot is showing basically replicating a Hook-Brown curve by using this new curved Mohr Coulomb model. You can specify a table of points that dictates what that line looks like. So again, it's super easy to do like a bilinear Mohr Coulomb model or something like that. You can define these points either in principal stress space, so sigma 1 versus sigma 3, or if you're a soils person, you might prefer shear stress versus normal stress. You can do that too. So this is a super flexible way to define different types of failure envelopes. Another thing related to constitutive models is, for those of you who use strain softening models, you will know that there's a plastic strain parameter that dictates where you are on the softening slope. This is great, but there are people out there who want to get more detailed information about the plastic strain. A lot of these people are doing analysis of seismicity, so you want to look at the nature of the failure and then turn that into some sort of seismic information. And so we've added, instead of just a scalar that tells you about the plastic strain, there's an entire tensor that tells you about the plastic strain. So you can just get more detail about the nature of the failure that's occurring. Okay. The features that I'm going to talk about now, a lot of them are related to Sketch. And so it'll just be better for me to show it in the program rather than show it through PowerPoint. So I'm going to start up FLAC 2D now and show you some of these features. First, things that are related to Sketch also apply to FLAC 3D, because of course you can extrude your model and make a FLAC 3D model, but I'll just run it in FLAC 2D. That's probably where most of these things are most useful. So let's break out of PowerPoint here. Let's open a FLAC 2D. I've already got one open here, and here's a blank sketch. Okay. So let's start by building some sort of model. Okay, so we can go up here. There's this slope wizard. This is not new. You've probably seen this before. Let's make some sort of slope with a couple of benches. You can change these parameters to get different, shapes and so on. In this case, we'll just use the defaults. The only thing I'm changing here is I'm unchecking this box to create internal edges, because what I'm going to show next is creating joint sets in this model. And so we don't need the internal edges to create a nice structured mesh. We're going to fill it with joints, and it's going to create a whole bunch of edges doing that. So I uncheck that. I say, OK. There's my slope. I use Control-R to zoom in here. Again, this is nothing new. The new part comes now. So I go to this drop-down, and there's a new entry here called Joint Set Wizard. I open this up, and what I see is something that looks a lot like UDEC. Okay? This allows me to create edges in the model that I will then potentially turn into joints, zone joints, or interfaces in a FLAC 2D or FLAC 3D model. So this is just an easy way to create joint sets, almost exactly like you would do in UDEC. So I start by choosing the region where I want to create the joints. So I choose closed polygon, hit select, and I can choose my slope that I've already created. And this is pretty cool because this shape doesn't necessarily need to be convex like it would do in UDEC or 3DEC. As long as it's any closed shape, I can fill it up with joints. So I choose this closed polygon. I can give the joint set that I'm about to create a group name. This will be useful later if I want to assign properties or whatever. An origin, discontinuous or continuous, and then I start filling in these parameters. If you don't know what these parameters are, you can look at this little picture here, right? So let's say I want a joint set at an angle of 30 degrees. And this means that the joints will be angled 30 degrees counterclockwise from horizontal, right? So there's my angle. Trace length, let's say 4. But let's say I want some randomness here, right? So I can choose this little checkbox here to make some randomness. And then I can fill in standard deviation. So trace length of 4, and let's give it a standard deviation of 1, a gap length of 1, and a standard deviation of, let's say, 0.25. And let's say a spacing of 1 with a standard deviation of 0.5. So I'm going to create a joint set with some sort of randomness. Now, when I hit OK, it's going to create the edges and the points and everything necessary to create that joint set. Depending on how big your model is, that might take a little bit of time. So maybe you just want to look at it before you create the edges, just to make sure it's working. So I hit preview, and I can see what those joints look like before I actually generate the nodes and the edges. This looks okay to me, so I hit OK, and now it actually does the business of creating the nodes and the edges. So cool, easy. I just created a joint set. It's got some discontinuities. It's got some randomness. Fantastic. Maybe I want another joint set, so I can go up here and do the same thing again. I need to choose my closed polygon. Maybe I want to give it another group name, because maybe I want to have different properties for this joint set than the other one. So let's call it joint set 2. Let's offset it a little bit. Let's choose an angle of 100 degrees this time, so it's almost vertical. Let's give a bit more randomness to the trace length and a bit more randomness to the gap length. Spacing will leave the same. We can skip the preview this time. I'll just hit OK, and we'll see what happens. Boom. So there's the second joint set. You can see it automatically did all the intersections and everything. Fantastic. Okay, so there's the joint sets that I created. Now, here's another new feature that I'm going to talk about, is related to cleanup. When you create these joint sets, you often end up with really small little edges, right? Especially when you add randomness, you can end up with little tiny edges. That's going to be a problem when you try to create zones. So I probably want to get rid of this kind of situation here. And I can do that with this automatic cleanup tool. So I hit the broom. I can choose merge points. And I can say, for example, all points within 0.1 meters of each other. I'm just going to merge them together. Boom. And so those 3 points just became 1 point. And now my life will be easier when it comes to zoning. Another new feature. What happens when I create these joint sets, these edges all end up in they all have a group name, and they all end up with a certain slot. And so let's show the controls here. And this concept of assigning slots in Sketch is a new thing. So let's click on one of these edges. You can see by default, things go into slot construction. This is the same as it used to be. You had no choice. They always went to construction. Now I have a choice. So when I created these joint sets, they went into a slot called joint set. And so you can see that this group name is joint set 1 in slot joint set. If I click on one of these almost vertical ones, you can see it's got the group name joint set 2 in slot joint set. So I have the ability to specify different different slots. And I don't even have to use the predefined ones. I can make up my own. So for example, if I choose one of these edges, and let's say I want to create a new slot and call it boundary, I can do that, and I can give this a group and call it top or something like that, right? So I can have a lot more control over the groups and slots, and not just for the edges, but for the different pieces of the model when I actually create it, if I had different layers or something like that. Okay, so I'm probably happy with this. Then I would go about specifying zone size and zoning it, and then I can just separate these faces and create zone joints or interfaces and use them as faults. Okay, that's all I'm going to say about Sketch. I'll now move on to some other new features. These are not specific to FLAC 2D, but since I'm in here already, I'll just talk about them now. Okay. Here I'm looking at Sketch. If I go to this blue drop-down, there are different things I can look at, plots and data files and so on. There's a new entry here called Rapid Tools. The plan here is to start adding more and more of these Rapid Tools. Right now we have one. So if I go to Rapid Tools and I choose Rock Slope, let's hide the documentation. All right, what am I looking at here? I'm looking at a slope. Got some sort of geometry. It's got a height and an angle. It's got a water table. It's got some properties. Okay, this is hook brown material, so GSI, unconfined compressive strength, and so on. For this geometry and this water table, and this set of properties, this slope has a factor of safety, an estimated factor of safety of 1.8. Okay, that's cool. Note that I didn't run a model here. It just came up with this factor of safety based on these properties. And now what's cool is I can start changing these parameters and see how the factor of safety changes almost instantly. So let's, for example, make this weaker by reducing the UCS. I can see that as I'm doing that, this factor of safety is decreasing. Okay, the weaker rock, lower factor of safety. Same thing here, for example, let's increase the slope height. As I make this slope height bigger, it decreases the factor of safety. Now, what's behind this magic? It is, of course, machine learning. So what we did here is we ran thousands and thousands of FLAC 2D models with all these different parameters, and then used some fancy machine learning to develop this widget so that you don't actually have to run these models to get the factor of safety. It's querying all of this data that was accumulated by running these thousands of models and using this fancy machine learning to figure out what the factor of safety is for the set of parameters that you specify. And so there is a little bit of calculation going on behind the scenes here, but it is, of course, not as much as would be required to actually run these models. And we worked out that to get the factor of safety with this widget is about 3 million times faster than it would be to actually run the FLAC 2D model and get the factor of safety. So this is just a very cool way to quickly see the effect of different parameters, to get a quick estimate of factor of safety for a set of parameters and a certain slope geometry, and so on. This slope might be a little simpler than you would actually want to run in real life, but again, it gives you a sort of a very, very quick visualization of how these different things affect the factor of safety. And then if you want to dig into the details and maybe change something outside of what you can do with this widget, I can actually just create the FLAC 2D model by pressing this button. It creates a Python file. In a future release, we'll have it set up so that it creates an actual data file. For now, it creates a Python file. You can see it here. Let's make this a little bigger. Here's all the parameters that it pulled from that widget. It makes the model. Here's the commands to create the sketch set, assign the properties. Here's the commands to set up the boundary conditions and then do the factor of safety analysis. So I can actually just run this Python file. Let's have a look at what's happening. Right, so now it's into the factor of safety calculation. And have a look at the model that was created. Here's the slope that was created. So again, you could use this as a starting point and then go in here and change things and mess around with the model and so on. Okay. So that's the machine learning widget. And again, our plan is to start adding more of these things. Right now we have this Hook-Brown slope. Our plan is to start adding more things like this into that Rapid Tools entry. Okay, next topic. Another thing we've added here, if you go to Help, and there's a new entry here called Itasca AI Assistant Beta. This is a new thing, so we're kind of testing it out. If I click on that, it opens up a web page, which is our own Itasca AI Assistant. So by now you will probably be familiar with these types of things. It looks a little bit like a ChatGPT type of thing. However, this is trained on our documentation and as many fish functions as we could find. This is not querying the entire internet looking for information about Itasca software. It is using our documentation as the training material, plus a bunch of fish functions that we fed to it. And it's using that to answer the questions. Our plan is, of course, to add more and more training data to this thing. Right now, it's this sort of beta version that relies on our documentation. But it's still super useful because it can reconfigure some of the things in the documentation to give you more specific answers. And it also allows you to ask questions in plain English, of course. So if we just do some sort of test here, for example, how can I apply fixity boundary conditions in FLAC 2D? We'll go off and think about it for a little while. And again, it's just querying, essentially our documentation. But you can see here it's giving me a pretty decent answer. In FLAC2D, you can apply fixity boundary conditions using zone face apply velocity command, which is correct. And it shows you the actual commands that you could use here. It gives you a little bit of extra information. And usually it will tell you, it will give you links to the location in the documentation where you could go off and get more information. And then it gives you, of course, a little warning here at the bottom that says AI-generated content may be incorrect. By now, we all are aware of the fact that these AI models can sometimes hallucinate. So we do encourage you to use a little bit of caution when you're using this thing. But it does give you a good starting point. And in general, it gives you a link to a location in the documentation as well, where you can get more information. Okay. That's all I'll say about the AI assistant. I encourage you to try it, and we're definitely happy to get some feedback on this if you see things in here that are kind of weird. Okay, one more thing to show in the demo. I've got a different FLAC2D model here. So let's pull that up. This is an example from the manual. So this is not new. This is just an example where we have a tunnel excavation, where we're excavating it in stages. It goes top, left, right, bottom. After each stage, we're adding support. So there's liners and there's cables here to support this tunnel. This is a pretty big tunnel. I can't remember. It's maybe 10 meters across or something like that. So it requires support. And there's nothing new here. So let's go to the final state. So we've excavated the tunnel. We've added the support. You can go and look at the support. So there's a plot here for cables. You can see here the cables showing axial force. This is not new. But what is new, if I look at my cable axial force plot item, there's a checkbox here for bar. And I can check that, and it plots bars, essentially a histogram on top of each cable element. It gives you a very nice visual representation of these axial forces. And it doesn't have to be axial force. I can choose anything else from this drop-down here. And what I get is these histograms showing me the quantities that I want to plot. And it's just a very useful visual representation of what's happening on these cables. And it's often a little bit easier to see what's happening than the case where it's just contouring. This is something that used to exist in the old FLAC, and we've now added to the new FLAC2D. It doesn't have to be just cables. You can do the same thing with liners or beams. If I go to my liner plot, so here's the beams showing the axial force, and I can do the same thing. I can click on the bar to get that histogram. In this case, maybe I want them to be a little bit bigger, so I can scale them, make them twice as big. And again, I get a very quick and easy visualization of what's happening on these beam elements. One more thing related to structural elements. Again, something that was in the old FLAC that we've now added to FLAC2D is these moment thrust diagrams. If you're a structural person, you will be familiar with this already. What this is taking the structural elements, in this case the beams, working out the thrust versus the moment and plotting them as little X's on the plot. You can choose what you want to plot here. You don't have to plot them all. You can choose by group. In this case, we're plotting them all. And then what you often want to see is where these plot relative to the strength of the elements themselves. And maybe when we ran this model, we didn't actually assign them a strength. We just assume they're elastic. So what you can do here in the plot item is you can specify a compressive strength and a tensile strength, a couple of other parameters, and it will work out these factor of safety diamonds, right? So 1.4, 1.2, 1, and you can see where your beams land within these factor of safety diamonds. In this particular case, you can see that most of them are within the 1.4 factor of safety, so I feel good about that. Maybe I'm worried about this guy out here. I might want to go and investigate what's happening with that one in particular. And again, this just gives you a very quick and easy way to look at, how your structural elements are behaving, and maybe allow you to investigate the ones that are maybe misbehaving, or the ones that are need a little bit more investigation. Okay, one more thing before I leave the demo. So you probably, if you've used FLAC2D or FLAC3D, you will know that I can do a split here. So maybe I want to look at two plots at the same time. So let's say I add the plot of cables on here. And now let's say, oh, shoot, I actually wanted the cables on the left side and the moment thrust diagram on the right side. I could go and close this one and open that one and reopen that. And then, you can do that. It's kind of a pain. So what we've added here is if I just click on the divider, if I right click on the divider, I can just say switch, and I can switch these two things. And then this can get even more sophisticated. Let's pretend now I split this plot. So I'm looking at three plots at the same time. Let's add the liner plot here. And now maybe I want those two plots on the other side. I can just right click on here and say switch everything. Or maybe I want to switch these ones above and below. I can just switch those two guys. And so just adding this right click functionality makes things a little bit easier when it comes to moving these plots around. Okay, that's all I'm going to say in the demo. I'll close FLAC2D. We'll just go back to the PowerPoint. So here's all the things I talked about: the joint set maker and sketch, the rapid tools, the AI assistant, the bar charts, moment thrust diagrams, tile manipulation. Just a couple of other things to finish off here. We've had people asking us about speeding up the model new and the model restore. A lot of our own consultants like to restore a model and create plots, and then restore the next stage and create plots, and restore the next stage and create plots. And when you have these big 10 million zone models, that can take quite a long time. So we spent some time trying to figure out how to speed up the model new and the model restore. And so essentially the bottom line here is that if you do a restore, it's about 3 times faster than it used to be. So, if you have one of these big models and it used to take 3 minutes to load it up, it now takes 1 minute. And if you're doing this 50 times, that time saving can be significant. In 3DEC, we've added implicit flow for the joints. So those of you that have done joint flow calculations in 3DEC will know that sometimes you can end up with a very small time step, and it can take a very long time for the fluid to flow through these joints. We've added an implicit calculator here so that you can do the fluid flow calculations about 30 times faster than we used to be able to do. And then the last thing is just the ongoing effort to try and make everything available in Python. There are still a few things that you can do in Fish that you can't do in Python, and we're gradually bringing everything into Python. And in 9.2, we've added this zone field data. So that's just another thing you can now do in Python. So that's really the end of the 9.2 webinar. Now is the time for you to ask questions, and we're happy to hear them. Thanks for joining, and I hope that was informative and useful for you.